Hello dear student, welcome to the video Nonlinear Raman effect. Nonlinear Raman effect is a nonlinear effect of whatever we have seen in the Raman spectroscopy. The Raman spectroscopy was successful in explaining many of the molecules which was not visible in IR or vibrational Raman spectroscopy, while it had some limitations. So, nonlinear Raman effects or many of the variations were tried with the Raman spectroscopy, and one of such variation is changing the source of radiation or the source of input. And by changing the source of input to a coherent source, that is a laser, we get nonlinear Raman effects. In this video, we will talk about nonlinear Raman effects, the harmonic generation, hyper-Raman effect, stimulated Raman effect, and coherent anti-Stokes Raman scattering occurs. The nonlinear Raman effect is observed when we change the source of radiation to a laser or a coherent source, and this led to new scattering processes. The development of a high-intensity laser system has led to several new scattering processes. A very high electric field intensity are associated with the monochromatic radiation produced particularly by a giant pulsed laser such as ruby, and the output of the giant pulse laser such as say in the neodymium glass laser system consists of a pulse which exceeds over say 10 to 100 nanoseconds. It is for a relatively short duration. The pulse which had a very high output power of about 10 to power 5 watts or higher. When the electric field of this intensity is being irradiated to a molecule for this very short period of time, we have observed nonlinear effects, because this nonlinear field will significantly interact with the molecular polarizability. Earlier when we have studied Raman effect, we have considered polarizability, but we have considered only the first term and we have neglected the higher order term because they were ignorant, were insignificant. But in the case of a nonlinear Raman, since we are using a source of a very high intensity, these nonlinear terms also come into play. Therefore, for a sufficiently intense excitation source, we use the polarizability of the molecule change as P is equal to alpha E plus half beta E square plus 1 by 6 gamma E cube, etc., and they are denoted by the polarizability of first order, second order, and third order. We know alpha is polarizability, and beta and gamma are called second and hyper order polarizability, or they are higher order polarizability. The beta and gamma are tensors of a rank 3 and 4. The value of alpha, beta and gamma are 10 to the power 40, 10 to the power negative 40, 10 to the power negative 50, and 10 to the power negative 60. The quadratic and the cubic term becomes important when the large intense electric field intensity of the irradiant of the incident radiation is being affected. When the dipole moment of the molecule P get affected in the same order as the permanent dipole moments. So this is an effect we see when the dipole moment induced become equal to the dipole moment, the permanent dipole moment. Effects due to the second and higher order terms in the series are referred to as non-linear effects because they arise from the terms which are non-linear in E square, E cube, etc. These effects are usually small but a very high power laser, and hence the electric field E characterizes the laser radiation, causes them, and they make them very important. Many novel phenomena arises as a consequence of nonlinear interaction of the molecular system with an intense radiation, and all phenomena involve changes in the frequency of the laser radiation, such as what we see in the normal Raman spectroscopy. In normal Raman spectroscopy, the input radiation is being changed by interaction of molecule. Just like that, here the input radiation, which is a laser, and the intensity of that laser is changed with respect to different changes with the interaction with the molecule. And in this video we will observe three different types of nonlinear Raman effects, that is hyper Raman effect, the Kars and stimulated Raman effect. Before that, we should know what is a second harmonic generation. You have already seen second harmonic generation in nonlinear optics. So similar to that, we should sketch what is second harmonic generation or frequency doubling in the case of a nonlinear Raman spectroscopy. We know that the magnitude of an oscillating electric field is given by the formula E is equal to A sin 2 pi nu t, and this nu is the nu of the incident radiation, or the frequency of the incident radiation. When we square the term, we get E square is equal to A square sin square, which will give you 1 minus cos 4 pi nu t. Here the frequency of the radiation is being doubled. We know that the nonlinear interaction term contains the term E square, E cube, etc. So when we consider the second order polarizability, we can see that the frequency term is being doubled, and this is known as second harmonic generation or frequency doubling. In higher order terms in the equation, we see the third and the fourth harmonic generation. There are several pure crystalline material which is used for frequency doubling. For example, ammonium dihydrogen phosphate or potassium dideuterium phosphate, etc. are materials being suitable for incident radiation for a limited wavelength range in the visible radiation. The importance of these materials in the laser operating is in the visible region can be made to operate in the near ultraviolet region also. The efficiency of frequency doubling is quite low, often a very few percentage, but it may be as high as 20 or 30% in some cases. Now let us step into the first Raman effect, nonlinear Raman effect, that is hyper Raman effect. In a normal Raman effect, an incident radiation is absorbed and the molecule goes to a virtual state, and then it decays to a lower energy state or higher energy state, giving you the Stokes or anti-Stokes lines. In case of hyper Raman effect, two photons of similar radiation omega 0 is observed to go to a virtual level of 2 omega 0, and it decays as a one photon to a vibrational state, emitting a frequency 2 omega 0 minus or plus or minus Vm. So here we observe another radiation which is non-coherent radiation is emitted, which has a frequency. Earlier it should be a frequency of omega 0 plus or minus omega m, but here the frequency we observe is 2 omega 0 plus or minus omega m. And this causes because of the high density of photons which is available from the high intensity laser. Here the two photons of high intensity of a frequency nu 0 is absorbed and the 2 nu 0 transition occurs. When the incident radiation provides a sufficiently high density of photons, two photons of frequency nu 0 are simultaneously scattered to create a new photon of energy 2 nu 0, or a photon of frequency 2 nu 0 plus or minus nu m is observed. Here nu m is the frequency of the molecular vibrating system, giving rise to Rayleigh scattering, Raman scattering in vibration system. This phenomenon is known as hyper-Rayleigh hyper-Raman scattering and anti-Stokes Raman scattering. Here the Vm or plus Vm or minus Vm stands for Stokes and anti-Stokes hyper-Raman shift. The hyper-Raman scattering is extremely weak. These transitions involved in hyper-Raman and hyper-Rayleigh and hyper-Raman scattering can be seen as a phenomenon of second order induced transition moment. We have already seen that the vibrational transition causes because of the polarizability. Therefore we see it as a phenomenon of here hyper-Raman is a phenomenon of a second order induced transition moment, and it is given by this equation. Here BFI is the transition hyperpolarizability and E is the electric field of incident radiation. The intensity is proportional to the second order polarizability, so it depends on e to the power 4. Like Raman scattering, hyper-Raman scattering is incoherent and is proportional to the number of species. Hyper-Rayleigh occur to the molecules. We have different selection rules, and these selection rules depend on the symmetry factors which determines the components of B. B has an 18 component tensor, so it depends on the symmetry factors which determine the value of B. So selection rules are different from that of Raman. The sum of the hyper-Rayleigh lines are not seen in centrosymmetric molecules. In centrosymmetric molecules, these lines are absent. Therefore, we can use hyper-Raman to actually find the molecules or give a trace of the molecules with a centrosymmetric cell. And these are the certain inferences of hyper-Raman effect. That is, vibrations allowed in infrared are also allowed in hyper-Raman scattering. The molecule with a center of inversion, all hyper-Raman active vibrations are antisymmetric to inversion. Unlike polarizability alpha, the hyperpolarizability beta can be 0 for molecules with a center of symmetry, and thus the hyper-Rayleigh scattering can be absent in some system. Further, those vibrations which are also infrared active can be distinguished in a hyper-Raman spectrum since they are always polarized. In some systems, transitions that are neither infrared nor Raman active are allowed in hyper-Raman scattering. In fact, these vibrations sometimes appear in the Raman spectra in condensed phase, which has been attributed to hyperpolarizability effects. In a normal Raman scattering, the spherical top molecules do not exhibit pure rotational spectra, although it is allowed in hyper-Raman effect. Hyper-Raman scattering can be observed in all three states of aggregate. However, due to extremely weak nature of hyper-Raman, it is found only limited application. We can also get into the third order of hyperpolarizability or third order transition moment. If this come into play, the lines observed by this will also be very low, but if this come into play, we will get lines of intensity 3 nu 0 for Rayleigh, and for Stokes and anti-Stokes 2 nu 0 plus or minus a nu m can be observed. But this is of a very low intensity and it can be ignored. The second type of nonlinear Raman effect is a stimulated Raman effect. If the Stokes or the anti-Stokes radiation we observe is sometimes become coherent and intense, so that it is intense enough to stimulate another transition in the same molecule, then this effect is called stimulated Raman effect. So the stimulated Raman effect come into play when the Stokes or the anti-Stokes radiation are intense enough to stimulate another transition to get stimulated Raman effect or stimulated Raman spectra. So for stimulated Raman spectra, we will get lines nu 0, that is Rayleigh. Then we will get nu 0 plus or minus nu m for our first Stokes and anti-Stokes. When those lines are absorbed and emitted again, we will get nu 0 plus or minus 2 Vm and so on. So the lines we observe will be nu 0 plus or minus n Vm. So every line has a constant separation of Vm is observed in the stimulated Raman effect. Unlike Raman effect, the transition or the output radiation here is coherent. In other Raman effect we have seen is in non-coherent, but here the transition is stimulated. Therefore, the transition here, what we get here is coherent radiation. That is, the output is also a laser. Since it is coherent and intense, it is capable enough to make another transition in the same molecule. The first Stokes line of the stimulated Raman is seen in a nu 0 minus nu m, and they become sufficiently powerful radiation for nu 0 powerful radiation at nu 0 minus nu m, and it produce line nu 0 minus 2 Vm and so on. So we have lines of constant separation. Stimulated Raman effect is a self-amplifying effect. The intensity of the successive stroke, say up to n is equal to 3, has an exponential decay relation. The frequency of the higher harmonics, or what we call as overtones of the first frequency line we observed, is in the ratio 1:2:3, etc. That is, all lines are equally spaced. The anti-Stokes lines can also be observed under suitable laboratory conditions, but this is very weak. The stimulated Raman lines are observed in forward emission, that is in the same direction as the incident radiation. So we keep the probe about in a range of 10 degree with the direct in to the line of the incident radiation. We can observe the simulated Raman effect. At high intensities, Stokes radiation can influence the molecule. The laser of frequency nu0 and the Stokes radiation nu-s couple each other and result in an intense stimulated Raman scattering signal, and this is used in obtaining monochromatic light sources for specific wavelengths. It is also used in the study of lifetimes of vibrational state. This gives us information about lifetimes of vibrational states. The last type of nonlinear Raman effect we study today is a coherent anti-Stokes Raman scattering or CARS. As the name indicates, here the radiation is coherent, here the radiation is anti-Stokes. So coherent anti-Stokes radiation or CARS is obtained when two coherent laser beams of sufficiently high intensity of a frequency nu0 and say nu-t, where nu0 is greater than nu-t, coincide inside a molecular medium, that they interact inside a molecular medium, and a new type of frequency is generated. This new type of frequency is given by nu-a is equal to nu0 plus nu0 minus nu-t, that is 2 nu0 minus nu-t. If we adjust the probe such that nu0 minus nu-t is equal to the almost become equal to the vibrational or rotational states in nu-m of the molecule, then the scattered radiation occur at nu0 plus nu-m, that is here we get an anti-Stokes line. Strong coupling of the intense laser field and the anti-Stokes field are generated inside the molecule and can be observed. The emission nu-a is coherent and it is anti-Stokes with respect to nu0. Hence we have the name coherent anti-Stokes Raman scattering. So the process is two coherent radiation nu0 and nu-t are focused collinearly in a molecular medium. We have a pump and we have a probe. When the frequency nu-t is varied by keeping nu0 a constant, such that at some point it becomes a nu0 minus nu-t is equal to nu-m, then another radiation of nu-a, which is equal to nu0 plus nu-m, is generated in parallel to the incident radiation. And these anti-Stokes radiation can be filtered from our incident radiation nu0 and nu-t using interference filters. If nu-t is varied in the vicinity of a nu0, then we can have all Raman frequencies such as Raman frequency at nu-m, 2 nu-m, etc. can be observed. Even if we do not make nu0 minus nu-t equal to nu-m, this CARS can be observed but with a reduced intensity. If two photons of nu0 are absorbed, just like in hyper-Raman, if two photons of a nu0 and one photon of a nu-t is absorbed, then another radiation, say nu-s, which is equal to nu t minus nu m. So it is Stokes with respect to nu t is emitted, and this is called coherent Stokes Raman scattering, CSRS. In the coherent anti-Stokes Raman scattering, the energy of the system will remain constant. Only an energy exchange between nu 0 and nu t occurs here. The molecule does not absorb or give energy to the system. Cars has different advantages and disadvantages. The advantages of the cars is that it has a very intense line, therefore there is no detection problem. The cars experiment, the intensity of the car signal is 4 to the 5 magnitude orders of intense. Thus car spectroscopy, there is in general no detection problem. The car signal can be discriminated from the light resulting from other processes such as fluorescence and thermal emission. The car's spectroscopy reveals a high resolution which is determined by the line width of the lasers nu 0 and nu t. The cars is used for low concentration determination in the range of micrograms. In case of a non-resonant cars, the detection limit is in the range of 0.01 to 0.05 micron. There are some disadvantages for cars. Cars can only be performed with high experimental effort. In order to carry out cars experiment, it is necessary to avoid any signal fluctuation caused by the intensity and frequency instabilities of laser or due to the changes in the spatial overlap of the excitation laser beams. The band shapes are often distorted. The samples are likely to be damaged by focusing high power laser beams. The non-resonant background can be troublesome. It may be difficult to maintain the required coherence of light beams over anything for a short period of time. The CARS is important tool for molecular structure studies and analytical chemistry. It is a useful technique for the study of biological samples in aqueous solution, which often produce strong fluorescence in the normal Raman scattering. And we have a lot of application in CARS of rotational spectra of gases. In particularly useful application in car spectroscopy is as a probe of species present at high temperature combustion source. Many new applications of CARS in molecular beam studies, plasma diagnostics and energy transfer are also observed. By this we have come to an end of this chapter. I have used this text of D.N. Satyanarayana, Vibrational Spectroscopy, Theory and Application, published by New Age International Publishers, to make this video. Thank you for listening.